Hi, Ariman here. So before I get into the slides on computer architecture, I just want to briefly talk about my idea of what a computer is and how we realize this, right? So my idea of what a computer is, firstly, a very black box interpretation, being that a computer is a device that has some inputs, some memory, and it processes these inputs using combinational and sequential logic to give firstly transform the memory, and secondly produce outputs, right? So traditionally, the laptop computers we use, the inputs are like keystrokes and the mouse clicks. The memory is, of course, the memory stored in the computers. The inputs can be transformed into, for example, writing a text file and saving it on the computer, or it can also be transformed into things like playing a game where the what we see on the screen is in fact the output of the game, right? So in some sense the computer is processing the inputs we have, the memory it already has, to transform the memory, store different things, delete old things, and to uh, produce some output. So very black box picture of what a computer does. Now how exactly, what do we need to do to be able to achieve such functionality, right? What does the processing entail? What type of processing do we want to do? What type of processing can a computer do? So essentially, a computer is something that we want to be able to program to do certain functions, to perform certain instructions. So essentially what we want the computer to be able to do is, we want to be able to program the computer to implement some form of a finite state machine. So if I want the computer to, say, add up certain numbers in some order, then I want the computer to be able to go from one state to another till it finishes adding the numbers and display that on the screen. And I want the ability to be able to program what these states are, when it will move from one state to another, and show the output. So essentially, uh, the ability to program the computer into performing the task of any finite state machine is what, in my opinion, makes it a computer. And essentially any output we have is just some finite state machine on all the inputs and memory that the computer already has, right? So anything that a computer does can be viewed as a finite state machine. So if we can figure out a way to implement a finite state machine on hardware, we can figure out a way to talk about how computers work, right? So now how exactly is this Mealy FSM in principle implemented by this memory and sequential logic and combinational logic, right? So the first part of the Mealy FSM are the states itself, right? So we have the present state and the next state, and we know that on the clock cycle, next clock cycle, we have to go to the next state. So given let's assume a Mealy FSM. So given a present state and some combination of the inputs, we want the computer to produce some particular next state, right? So what that entails is, number one, we need the ability to store the present state somewhere, which is provided to us by the memory capabilities of computers is in storing things in things like registers. Number two is we need some logic, combinational logic, to determine what the next state should be. So we can think of it like a game where you're viewing some animation, and based on your keystrokes you're going to different rooms and maybe shooting people and they're dying, etc., etc. So it's all based on your inputs and the current state that the next frame probably depends on, right? So once you have the ability to store this current state and have some blocks of combinational logic to determine based on the current state and the inputs the next state, and you have the ability to basically go from this current state to the next state at every clock cycle using some sequential logic. This is almost there to the computer, but the only missing ingredient is your ability to program, right? So where does this ability to program come in? So you can very well implement this on a single circuit where you have the exact combinational circuit for every next state logic, right? But that's not very useful. So your ability to program, somewhere or the other, it comes from the fact that the computer has some circuits in its CPU which correspond to computations that it is capable of already doing electronically, and it has the ability to follow instructions and to perform these calculations on data that is stored in registers. So if you can from this basic hardware abstract up to the problem that you want to solve, which is of implementing some particular FSM, then it becomes programmable, right? So essentially what the computer has, it has these fundamental circuits which can do some operations, and you can on data that is in some particular registers. So as long as you have a way to load data into these registers and perform those computations which can look like bit shifting, addition, etc., etc., and as long as you can abstract up from these computations to the type of computations that you want for your next state logic, you can implement any FSM, right? So for example, if your states are if you want to implement an FSM that just goes from state 1 to state 2 to state 3 to state 4 to state 5 to state 6, you somewhere or the other need to store these states in your memory, and you need to figure out a way to have some sort of a counter and have this addition circuit add 1 to the counter every time and access the corresponding register. So this is a way you can abstract up from the fundamental circuits that already exist to implement this kind of FSM. Of course, a very simplistic, not very well thought out example, but it's just to demonstrate that there are ways this can be done. So insofar as you can abstract up from this basic combinational hardware to more complicated things and implement any FSM, the computer becomes programmable to implement any finite state machine, and therefore it unlocks all the powers that a modern day computer has, right? because yeah, the you can basically react to inputs and memory to transform your memory and produce outputs. So yeah, that's some background on what a computer is, in my opinion. Hi, I'm Aryaman. I'm a student of EE 224 in the 2024 uh, autumn session. I'll just be covering these slides. These slides are prepared by Professor Alexander Stoichev from the Iowa State University, and like they cover basic computer architecture of a CPU that was developed in his class. So I'll just be covering and explaining these slides. So yes, this is the structure of the CPU that is developed by them in class, and it'll be referred to again and again in the slides as we try to understand the different parts of the CPU and their working. This gives us a general idea of the different lines available on the CPU. I'll get into it later. We can come back and refer to this diagram. So the basic convention is that inputs enter from the left and outputs enter from the right for each box. So for any box which you see in this entire design, if something is entering from the left, that's the input. Something's entering from the right, that's the output. The only exception is this control box where all the outputs are pointing down, but we can see throughout the CPU, the different control lines are going into different parts of the CPU. They're actually coming from this control box, right? So yeah, this was a course in digital logic taken by this professor, and the CPU was specifically designed for the course. There is also a software and hardware and simulator available for this CPU online. So the links of that can be accessed. And yeah, it basically simulates the running of a bubble sort program on the CPU. At a hardware level, how does it look? All right, so basic overview into all the components. We will get into the nitty-gritties of all of them in a bit. So this is the code memory. The code memory includes the instructions that the CPU will follow. Yeah, that's basically the purpose of the code memory. The CPU fetches instructions from here. Next is the opcode detector. So each instruction is associated with an opcode, and the opcode decoder. This opcode decodes which instruction has been specifically like the instruction that is fetched from the code memory. Which instruction or which operation code does it contain, corresponding to which we have to follow a certain instruction. So it's basically a decoder which will encode that instruction as a one in the bit corresponding to that particular instruction. Next, we have this control box. So depending on the instruction that we want our CPU to execute, we need to configure the different parts of the CPUs using these control lines. So we have a particular logic to do that. So this control box implements that combinational logic to execute different instructions on the same CPU. It's like the main idea of a CPU is that on the same hardware, you can like execute many instructions, and you can abstract these instructions to do more complicated procedures, right? So yeah, that's the basic idea of the control block. These are all the different control lines and where they go in. It's shown in this figure, and we can refer back to it later on. There are basically a lot of enable lines, select lines, etc. For uh, when this happens, we should select this particular register, or we should pull this particular value from this mux, or we should write onto this particular register, etc., etc. Yeah, that's the idea of these lines. So like for different type of instructions, we will enable different lines. Like if we want to read the value of some particular register onto the register A, we will choose the select lines according to that. The right select line C8 and C9 according to load the value into register A. Whereas if we want to load it into some other register, we'll change the right select lines according to that register. So basic idea is that the control lines can be configured to to execute different instructions. Uh, then we have some switches for the user input. So the user can manipulate parts of the code memory, and the user can also manipulate the data memory. So there are 16 switches for that. Uh, the value of the 16 switches manipulates the code memory if the write enable line of that is turned on, which is given by the control line C1. And correspondingly, the 8 lowest bits of these switches can also push data into the data memory by the user. If the multiplexer controlled by line C16 is pulled to 1, then that the value inputted by the user can go into the data memory. So the data memory basically consists of some stored data. The code memory consists of instructions for the CPU to run, and the registers in the center left of the diagram. Those registers are the values accessed by the arithmetic logic unit when it's dynamically executing some instructions. So if you want to add two numbers which are currently in the data memory, you first pull them into this registers and then you add them. So yeah, for any dynamic operation, those registers are used. So yeah, this is when we deploy it onto some FPGA hardware, etc. We map these 16 switches, and so we can control both the code memory and the data memory using the write enable line as well as the uh, select line of the multiplexer, depending on what we want to manipulate. Yeah, that's what they're saying. So the 16 lines are used for input into code memory, 16 switches, and the 8 lower switches are used for input into the data memory. Yeah, like I talked about the register file, so that register file is what is accessed for any dynamic computation. We pull data into that and then compute, and we store the result in one of these registers, and then we push that data back out into the data memory if need be for the future, right? So all the magic is happening in these registers. The data memory is just for storage. The code memory is just to process the instructions. The arithmetic logic unit is like it basically contains the circuits for the CPU to execute various types of logic. So it can have a, so depending on the instructions, it can have a circuit to add, it can have a circuit to shift bits, etc. It is purely combinational, and it executes the logics of the different instructions. And based on the control lines it gets, depending on what type of operation it has to do, it acts accordingly, right? Now, the flags register. So, we have certain flags like if you subtract a larger number from a smaller number, then you want some type of a negative flag to go. Sorry, you want some type of a negative flag to go high. So, yeah, we have flags like this, and we store the data of these flags in this register. And we have five different multiplexers to select from different areas, right? We'll get into them in this specific. So the program counter update logic is one of these. So basically, the program counter is what tells the it's what that's the logic that chooses the next instruction to be executed. So accordingly, that line of the code memory will be read. So yeah, so the that's the program counter update logic. And so generally speaking, after one instruction, we want to execute the next instruction. So we have some type of logic to add one to the current instruction and add one to the current address of the instruction and do that. But at times, we want to, like, for example, when we are executing a loop and we want to go back up to the first statement, we want to jump to a new step, in which case we need the address of that particular register in the code memory, in which case we want to so which of these two we want to do is controlled by the control line C2, the multiplexer corresponding to that. Yeah, we got into the data memory. So yeah, this is just some description of the different types of memory. Data memory is 16 bytes, code memory is 128 bytes divided into 64 addresses of 16 bits each. So data memory can be both read or written, and it has 16 bytes. It has a read port, a write port, and a write enable port. So yeah, this is just some specifics of the hardware implementation and the program that they have running as an example on the CPU, which is the bubble sort program. And now, obviously, so they're trying to represent the different values in the data memory in the register, but different values of the register or data memory on the hardware in by using LEDs. So they're only able to represent one digit. So that's why the only the last four LSBs are used to implement the digit, but like the data can be different. Like the last address where you see an 8, that could, with the 8, you cannot differentiate whether that is stored as an 8 or a 18 on the hardware, but it's just for demonstration purposes. On the hardware, we want to show it using LEDs. Yeah, this is how it looks. So ultimately, we want to sort these numbers, but these numbers are just the lowest digit. We don't know, for example, whether the second number from the left is 3 or it's 13. That's what they're telling us. And it we only use the first 8 uh, addresses of the data memory. So we don't know what is there in the rest of them, right? A code memory has uh, two parts. The first part is read only. So that is not subject to be tuned by the user. It has some predefined instructions. And the second part in BIOS mode can be written by the user, right? Now we get into the specifics of the, sorry, just give me a minute. So yeah, we have now going to get into the specifics of the opcode detector. So yeah, these are the types of operations in the CPU. You can read through them, but the main yeah, just an overview of some of them. So there's either no operation, in which case you don't want to do anything. You have types of inputs into the code memory, in which case you want to input some value into some register of the code memory. And everything you do into registers, you can also do with an offset, because the offset is basically telling you how many registers away you want to do this. So you, from the base register, if you want to input something into like 3 registers away, you can do that using the offset, right? You have operations which load immediate values from particular registers. You have operations to add, subtract, uh, then you have operations to store into the data memory, operations to shift bits, compare values. Then you have some of these operations which are there on the bottom of the scene. The jump and the different types of branches are there to jump or branch to a different uh, part of the like a different instruction, and not continue running the program sequentially. So you can either jump to some specific instruction, or branch, branch to some instruction in case some condition is met, which are there in the bottom operation. These are all given different codes. And when we write the assembly code, we can use these codes to kind of program this CPU. So yeah, these are all available in the assembly language, but in the machine language level, some of them are use the same uh, binary code, because there is some way to differentiate them from their subsequent bits, so we don't waste bits by giving them different codes. So this process is called aliasing. So for example, these two operations are aliased. We also have the branch if equal to and branch if zero operations, which are aliased. So I can give you an example here, which is that uh, if you want to check if the value in some stored in two different registers are equal, whereas you will, after giving the operation code, you will give the addresses of the two registers. Whereas if you want to check the value in one register, if it's equal to zero, you will just give the address of one register. So based on the number of bits coming later on the hardware level, it can be differentiated which instruction you are asking for. So these two are therefore aliased on the hardware level into a single opcode. Similarly, not equal to and not zero are also aliased. So this brings us to 23 operation codes, which the opcode detector detects. And whichever operation code it detects based on the inputs, it dis so the first 8 bits are to detect the operation code. And you may be wondering why 8 bits. If there are 23 instructions, you can do it with 5 bits. We'll get into that. And so the operation code detector, sorry, the operation opcode decoder decodes these 8 bits to decide which operation it it needs to be run, and accordingly makes that line one. So it's one hot encoding basically. But if you notice, the output from the opcode decoder is 27 bits. So why these extra 4 bits? We'll also get into that. Yeah, so this is the structure of the opcode decoder. So your first 4 bits of your instruction can theoretically correspond to, using this 4 to 16 decoder, 16 different uh, values, 16 different operations, but that's not enough. So we branch out some of these values to more decoders, like a 1 to 2 decoder and 2 to 4 decoders. And we use subsequent bits, which are the next 4 bits, some combinations of the next 4 bits to do that, right? So we're using mainly I8 and I9. So I10 and I11 are never really used for the operation. And even I8 and I9 are used for some specific operations. So yeah, why then do we need I10 and I11? The thing is that based on the operation we are doing, we want to have some control over which control flag, which control signal needs to be uh, changed in what way, ir, over and above the operation we are executing. So if your operation is loading into some of the register, you need control over which register you want to load into, which won't come purely from the operation, from the knowledge that you need to load. So for this, we are using these bits to select the registers. So that's also so that is the reason why we are sending 27 bits from the opcode detector, because the 4 bits which you can see that are represented by RX and RY, these 4 bits are sent additionally to change some select lines dynamically based on the operation we are executing. So the 2 bits of RX can always be used because they are not used to encode any operation, and the 2 bits of RY can be used for all the operations on the left side of the 4 to 16 decoder, because these operations are again not dependent on these bits. So for many of the operations, we get 4 free values we can use to change control some control signals, and for the rest we have the two values, right? So the rest of the 8 bits contain like the rest of the part of the instruction which is not related to choosing the operation code. So yeah, you have the 8 high bits going through the opcode detector. The lower bits go either into the ALU or into the data memory. So uh, if your operation is adding to some you're inputting some value which you want added to some some value stored in a register, you would send these 8 bits to be added to the ALU. Whereas if your operation is to store the value in the data memory, then you would route it to the data memory. So the two muxes controlled by C11 and C15 give you this option. And yeah, like we talked about, these 4 bits pass through but don't go through the decoder tree. So yeah, this is the abstracted version of the decoder, where we have these first 23 bits corresponding to the instructions, and we have 4 additional bits x1, x0, y1, y0, which we can use to uh, uh, change the values of some control lines directly based on the instruction we want to execute. So uh, the values of some control lines, which we talked about, like the registers we want to choose, etc., are not for them, it is not enough to specify what instruction we want to execute, but we also need to give some more specification which needs to be controlled. So we use these 4 bits to do that. We get into some example when it comes. So yeah, the first 20 at a given time, you will only execute one instruction. So these first 23 inputs are one hot encoded, which means that at a given time, only one of them will be one, rest all will be zero, which is intuitive. And the other 4 are not one hot encoded because they are just values which you want to pass through to control signals. That's how you get this 27 outputs from the opcode detector, right? Now we are getting into the control logic. So basically, based on the operation that you want to execute, the CPU designers have designed how you want to control these control signals, which signal you want on, which signals you want off. So all the signals for which there's no value, you want them off in this operation. And you can notice that there are some register specific control signals, which are like the select read lines and the select write lines, which for which you want to have some more control over, because just by specifying which instruction you're operating, you cannot fully execute that instructions. You need to know some more information. If I tell you that you need to add some values, you need to know which registers you want to add from, right? So that is specified by these x1, x0, y1, y0 variables by the user when they do this. So when the user writes in assembly that do this do this instruction on this particular register, then uh, it converts the instruction into the operation code, and the register into these it maps the x1, x0, y1, y0 bits to execute that onto the register, right? So if we go into an example, let's consider the uh, compare uh, instruction. So for the compare instruction, you have register port 0 select 1, registers port 0 select 0, registers port 1 select 1, port 1 select 0, as controlled by these x1, x0, y1, y0 bits. Now first thing I want you to notice is that in this operation we have compare over here in the first decoder. So for our CPU to know that it needs to execute compare, it already gets that information from the 4 MSBs. So we have x1, x0, y1, y0 free to give additional information. Now what these bits are encoding is actually in this, say we want to compare the value of register A to register C, then the first two, so C4 and C5 are controlled by X1 and X0, and C6 and C7 are controlled by Y1 and Y0. And we, using C12 and C13, we encode the ALU to show us the comparator circuit. So using this, basically we are comparing values in, say, register A and register C. So we would set C4 and C5 to 0, 0, and C6 and C7 to 10 if we wanted to compare the values in register A and B. So that's how we use these 4 bits X1, X0, Y1, Y0 to specify the registers which we want to do things to. So we may want to write to them, we may want to read from them. It's with respect to this register file. So whatever instruction we are executing, the register which we want to manipulate in that instruction is encoded in these 4 bits, right? So that's how so our entire control logic is purely combinational, and it basically uh, uh, it executes this particular control, that when you get when this particular bit is one hot encoded, then you need these lines to go up and these lines to go this way. So that is how the combinational logic works, right? And we can easily achieve that by just setting whatever values we need and ANDing them with the line that comes from the opcode detector, because we only want it to be executed when that particular line is 1, right? So yeah, this talks about how we are taking the bits from the instructions. And you can notice that we are also getting some input, this B1, B2, B3, and B4, which control this program counter mux. So again, as we spoke about, we want to use the program counter multiplexer to decide whether we want to jump to some other instruction. So these break commands, they use the flags to decide whether we want to break. So if we take example of break if negative, then sorry, break if greater, then if you subtract the second value from the first value, then the flag for negative will go up, and you want to then jump, so you set the program counter multiplexer to 1 so that the you're able to jump to some next instruction. And so yeah, that's why these particular values are computed using the flags register. Now, yeah, the control signals. So what are the different control signals doing? So C1 is just writing onto the is a write enable of the code memory. Just give me a second. C2 is again the multiplexer to choose for the program control logic, whether you want to just go to the next instruction or you want to jump to some specific instruction, right? And that which specific instruction you want to jump to comes from this 6 low. So you in the case you want to jump to some instruction, you use the 6 low bits and some logic if need be to jump to that instruction, or you use the 6 bits coming from the code memory itself. Like you use those bits and add 1 to them. That's what the program control update logic does. Then we have C3, uh, which is enabled to whether we want to go or no. C4 and C5, C6 and C7 we have discussed. C8, C9. So yeah, basically all these are different. You can see the purpose of all of these here. C1 through C18. I'll not continue getting through the individual, but they're all basically select pins, enable pins, etc. to do different tasks for the CPU. And they're written over here. Yeah, like C3 is the write enable for the program counter, etc. Now we have 5 multiplexers. We got into this program control multiplexer, which is to choose whether you want to increase increment the instruction address by one, or you want to jump to some other instruction. Then we have this C11, whether you want to pull from the code memory some value to load to the ALU, or you want to pull from the data memory. Then C15 controls whether you want to manipulate. Uh, Sorry, I misspoke in the last part. C11 controls whether you want to pull some value from the code memory or from the register file. C15 controls whether you want to import into the data memory something from the code memory or from the ALU. C18 controls whether this output which you're sending to the register file, whether you want that to come from the output of the ALU itself or you want it to come from the data memory. C16 controls whether you want the user to be able to input to the data memory right now or you want to pull the output from the register file. Yeah, that's basically the purpose of all the registers. And we get into how these registers, they're choosing 8 bits, so how they're actually doing that. So yeah, so we just take the inputs of each bit individually and pass the same control line to it. Yeah, and that's true for each of these multiplexers. This is a register file where, like we spoke about, the computation happens. It consists of an 8-bit parallel access register. So basically, it consists of many of these D D flip-flops, which on the clock cycle, if write enable is disabled, then it just passes through the feedback. And if write enable is enabled, then it passes through the inputs to the registers. So yeah, that is the parallel access because it accesses the inputs and gives the outputs parallelly and not serially. Yeah, this is all the different registers. This is again the multiplexers, same type of logic. All 8 bits use individual multiplexers, but they are all controlled by the same control lines because yeah, we want to do it parallelly. We don't want to pass one bit at a time through a single multiplexer. We want to do things fast, right? This is it's just repeating the same thing to for exhaustively covering all the components and to uh, in yeah. So this is the data memory. Now the data memory is also 8-bit parallel access. Code memory is actually 16-bit parallel access registered. So yeah, that was all that was covered in this particular lecture. There was some stuff that's covered in the next lecture, which he introduces in this lecture. He just tells you about what he's going to cover in the next lecture. I'll just also give a brief overview on what that is. So what does the arithmetic logic unit look like? So yeah, the arithmetic logic unit basically it just contains all the combinational logic to implement all different types of instructions, and it is controlled by these two control lines, basically telling it what it needs to do. And yeah, it takes inputs from these registers, and yeah, it gives outputs, and it just contains the circuits of all the different types of instructions it can execute. So adding, subtracting, etc. whatever it needs to do, it does. So the two lines means that you can choose between a set of basically four circuits which do different operations, and those circuits can actually be abstractions of multiple instructions that can be implemented. So you can have like a adder subtractor in one circuit and you just need one bit to switch between those operations. So yeah, that's basically how the arithmetic logic unit works. It's the computer, it does the computation in the CPU, the actual computation, and it contains the circuits to do that computation, right? Then we have the flags. So we get into what the flags are, the write enable signal of the flag, when you want the flag to be enabled, and essentially what the different bits of the flag represent and how you use them, right? Then we have the PC update logic, which I have explained multiple times in the past. It basically just tells the so the code memory has some select lines for which address memory has to be passed through, and the PC update logic kind of tunes those lines, right? So the PC update logic either increments the previous values of those lines by one, or which is when the control signal C2 is 0, or it uh, makes an entirely new instruction in which the control signal C2 is 1. So based on what the instruction is, when you want to jump or when you want to break, the program control update logic gives you some combinational circuit that allows you to do that. And this is your program counter, which contains the actual count of the register which you want the next instruction to uh, come from. And basically, when the next clock cycle happens, that time you do that instruction. And yeah, I think that's about it from this lecture. Talks about some industrial microprocessors. Yeah, and that's it. All right, that's it. Thank you for listening. Bye. Hi. I'm really sorry for the background noise. The dogs are running away wild. Yeah, but my objective for this part of the video is that I want to go through a simulation of the i281 CPU where it uh, runs a program. I want to walk through that simulation once again. Again, sorry for the background noise. Yeah, so this is basically a program that I've uploaded uh, onto the this is the simulator of the i281 CPU, and using the assembly level instructions, I have put a program that adds the numbers from 1 to 5. So like first something to note is that uh, the uh, assembly instructions have a one-to-one correspondence to machine code. So for every line of machine code you can see in the code instruction memory, there is a corresponding line of assembly code, right? The first interesting part to note. So yeah, I'm just going to walk you through how this CPU actually ends up implementing this. So first, what it does is it loads the value 0 into the B register. So load into B the value 0. That's what this instruction code stands for. So the 0011 stands for load, the 01 stands for which register we want to load into, and these two bits are don't care, and then this is the value that we want to load in, which is in this case 0. Right? So this is the first instruction that executes, and yeah, so I'm going to execute the instructions step by step to begin with. So yeah, this is the program counter. As you can see, the program counter is currently at this particular instruction. So that's what will get execute, and the value 0 gets loaded into this register. Now, how that actually ends up happening is that uh, you have these bottom 8 bits which go through this particular purple path that you can see, and this control C15 is set in such a way, C15 and C18 are set in such a way that it gets fed back to the register file, and that is the input that is received, and we have one enable wire for this register file and two wires to select the which register we want to write to, right? So that's how the value 0 gets written to the register B. Uh, Next, what we do is that similarly, we load the value 1 into the register A. So it's a very similar process, so I'll not explain it again. I'll just move on to this next instruction. After this, in the register D, we load the value that is stored in the data memory, right? So if you notice, the load here did not come with any offset. So it's directly going to load the value, which is the first value in data memory. And it just gives this a name n, right? So essentially what this program is doing is wanting to add the numbers from 1 to 5, basically. So right now n is 5. So this is some application of how we want our program to stop, right? So that's what essentially you're doing, is that you're loading into D this value from the data memory. Now that happens by firstly you have these lines here denote the address that you want to access of the memory, and that's how this read enable uh, kind of fetches this value out, and that's the output that you get. And C18 is also configured in a way that this gets fed back to the register, and the selects are configured in a way that it loads into D. That's how our control logic is written. All right. The next step is that we are comparing A and D, right? So A is essentially our counter, and so we want our loop to continue as long as A is less than D. So what we're doing is that we're going from the integers 1, 2, 3, 4, 5. We're storing the sum in B, so every time we'll add to B. And the moment A becomes equal to D, that means the uh, A becomes greater than D. It means that we do no longer want to add, we want to break out from this loop, right? So this is a comparison between A and D. So the next step is, of course, that we want to uh, break or bridge if greater to this instruction that is end. So if greater is checked by this by the flag, which is the negative flag here. So obviously if the negative flag goes off, that means A has become equal to D. Then you basically using these flags, we are able to figure out whether that happens, right? So essentially what we're checking for is that our negative we want this break if greater than to occur when your negative flag is 0 and your 0 flag is also 0, right? Because you want A to be strictly greater than D. So That's the logic that checks that. After which we have the so that end just ends the program and gives us an output, which once we run it, we see. After that, we just add B to A, right? I can just see that. That's the next step. So is that it? Yeah, the next step's there. Yeah, so yeah, something I forgot to mention here is that in this break if greater than, uh you move to end the end uh line of the code. So essentially what that does is you add some value to the program counter which gets you to that line. So it basically controls this program counter update logic, which instead of executing sequentially, it directly jumps to a particular instruction. In this case, the end is essentially uh yeah, so it uh 1 second. Yeah, it just breaks into the end. That's the point I was trying to make. Uh Now what we do is we add A and B, and essentially the control logic for the ALU is set so that it performs the addition, and C11 is also set so that what operation we are doing adds. And yeah, this is how essentially then we add 1 to A. We then jump back to the loop again by the program control update logic, and we repeat this till we end, and we have a stop at end flag which is checked. And I'll just reset and run this program and show it to you. And the final answer is obviously stored in B, and I'll just increase the speed. So yeah, this is the program finished, and the final answer, which is the sum from 1 to 5 of the integers stored in B, is 15. Yeah, just wanted a quick run through of that.